Get his cell number and call him at home. Later, the better. Every year, this without fail, somebody asks, "What do you do if it's exactly 0.05?" Right? It's not that important, really. I mean, it's really not that critical most of the time. Yeah, those first two boxes are a test for the equality of the variances. So you can decide whether to use the top row or the bottom row. The top row, all the calculations are based on the assumption of equal variances. The bottom row, all the calculations are based on unequal variances.
Like the Walsh pooling standard deviation?
I'm not sure. What did we bring up about Walsh before? Levi, when did Walsh come up before?
It's the unequal variance.
Unequal variances, yeah. Okay, so only a real statistician would know that that's called the Walsh variance. Okay, so at any rate, so let's try this again. Except this time, I'm going to open up another file that I have. Another file has the same averages, but the variabilities are different. Okay, so I'm going to open up that file. I'm not going to bother opening up in Excel. I'm going to go straight to SPSS, t-test, unequal variances. I'll click on that. Okay, there it is. Okay, so I'm going to analyze descriptive statistics, descriptives. Oops. Okay, I'm going to move them both in there because I just want to see the means. Okay, what do I wind up getting? Well, the means are 10 and 7.56. They're the same as the other variable, the other test we just did, right? Same means, right, for males and females. But look at the standard deviation. One is 2.7, the other one is 1.0. Remember what we said as a general rule, if one's double the other, maybe you want to consider using unequal variances, just because it's too hard for us to, or we're too lazy to do a real calculation on this. But SPSS is going to do it for us. Now, again, I'm going to have to restructure this data because this is really, I imported this from Excel, and it's not really formatted correctly for SPSS. So I'm going to go in here, 1, 1, 1, 1, 1, 1. One's going to represent females, and 2, 2, 2, 2, 2, 2, 2, 2. Okay, this very well could be this could be the order of finish in the elections tomorrow, is possibly right. 1 and 2. Okay, so the first column is our values, right? The ones that we're finding the means of. Values. Okay, and the second column is gender. Okay, oops, what happened here? What did I do? There must be some other junk in the other columns. Okay, so at any rate, okay, let me change this to scalar. Oh, I didn't, did I not? I'll worry about that later. Okay, that's scalar. Okay, and I'm sorry, I got that backwards. The gender is nominal, and the value is scalar. And let's see. For the values, I'm going to put in 1 represents female, and the value 2 represents male. Okay, so now if I go back to the data view, you should be able to identify which ones are males, which ones are females. Okay, so again, the average for males, the average for females is the same as it was before. The difference is, take a look at the variability for the males. Very little variability in there, right? Right? The female variability is about the same. But the variability of this group is quite a bit different than the variability of the first group. So let's go ahead, and I'm going to open an output window here so I can get to my analysis. Analyze. Does anyone else have that problem? Has anyone tried to do this and notice the difference in the two menus, whether the output window's open, the input window's on top? No? Just me, right? Okay. How about you guys online? Is that happening to you guys? Okay, analyze. I hate to reinstall this one because it is basically working. Compare means, independent sample t-tests. Okay, so let's see, the test variable, in other words, what I'm finding the mean of is the values. And the groups I'm breaking them up into is gender. I'm comparing males to females. I'm going to define the groups. 1, 1 represents males or females, 2 represents males. Okay, and I'm going to say okay. Let's compare these two means. See what the result is. Okay, so this time, let's start out by deciding whether or not we should use the top row or the bottom row. Okay, so the top row, let's see, my test for equality of variances. Equal variance is assumed. Okay, that's my null hypothesis. I'm going to reject that and use the bottom row if my p-value for the test of the equality of variances is less than 0.05. Is my p-value less than 0.05? It is, right? Can you guys see that? It's less than 0.05. So which row do I use? Use the bottom row, right? You would, and now you're doing the same calculation that if I had gone on to the next page, the next page has this data in it where we could use different formulas. I'll show you in a second. Okay, so let's figure this out. So what does the t-score come out to be? 2.511, right? They both came out to the same, didn't they? Okay, sometimes they'll be very similar. Sometimes there'll be a little bit of a difference. Now look, what's our degrees of freedom? That's a weird number, right? 10.1, right? That's kind of odd, right? Okay, and what is our significance? Can we reject the null hypothesis using the bottom row? What's the significance? 0.03. It's less than 0.05, so I can reject my null. What was my null hypothesis? That the mean for males is equal to the mean for females, right? I can reject that except my alternative hypothesis. Right, so I reject my null hypothesis again, except my alternative hypothesis. Okay, so now let's go back to that table, that chart, which gave us kind of a rundown on all the different ways that we might do this. Let's go in here. Let's see how that was calculated. See, we did the calculation for equal variances. Let's see how the calculation would go for unequal variances. Okay, scroll up here, and let's see. It's going to be equal to, for unequal variance, and not assuming equal variances, it's going to be equal to, t is going to be equal to x bar 1 minus x bar 2, no change, over the square root of the standard deviation squared, the variance squared, over the sample size of that group, plus the standard deviation squared of the males, one's females, one males, over the sample size of males. Add them together, find the square root of it, and that would be your standard error, and you just divide that in. A little bit simpler than the other one. We didn't have to calculate a pooled standard deviation, right? So that's simple, but what's not simple? How do you calculate the degrees of freedom? Remember before it was n1 plus n2 minus 2. What is it now? It's alphabet soup now, right? Right. So do we really want to calculate that? SPSS calculated, it came out to 10.131 or something like that, right? Sometimes what you might consider doing is taking the smaller sample size, 9, subtracting 2 from it, and just for the purposes of estimating whether or not you can reject the null hypothesis, call the standard error, call the degrees of freedom 7. Really turned out to be 10. That's very conservative, right, to do that. But yeah, if we're a larger sample, decent sample size, like 30 in one group and 30 in the other group, well, then it would wind up being, say 28 if you took the smaller group, right? And your real degrees of freedom might be 31, 32. Wouldn't make that much difference in a real example, most likely. So a lot of people would just simply say, I'm going to take the sample size of the smaller groups, subtract 2, and use that for the degrees of freedom rather than calculate this formula. What does SPSS do? SPSS has nothing but cycles, computer cycles, right, available. So it's going to actually calculate that formula every time it does it. Okay, so what we've looked at, let me do one more example. Remember that first one we started with? Let's do that in SPSS. How are we doing on time? We're in good shape, I think, semi-good shape. Okay, so I'm going to go back here, and I'm going to open up that file. That one is going to be less of a problem for me because that one's already going to be basically formatted, I think, the way I want it. Okay, there we go. It's a set of 9 numbers. That's all it is, right? Okay, so I'm going to compare that, analyze, compare. No, I still got to do that with the output window. You see what's happening, right? I'm getting a different menu, and I shouldn't. This is a one sample t-test now. I only have one sample, and I'm comparing it to a another population's known mean. So I'm going to move that number. What's the problem there? What does those like three different colored balls represent? Nominal values, right? Nominal, right? This is not, we don't want this, this is not a nominal variable. It should be scalar. Okay, good. Okay, so now I'm going to go again to the output. Open an output window. Analyze, compare means. One single sample t-test, I'm going to move this into the test variable, and then I'm going to put in here the value that I'm going to compare it to. When we used 8, we failed to reject the null hypothesis. So I'm going to put in 8 there. Okay, and let's see what the value of t is. T comes out to be 1.933. What's the probability of being wrong if I reject my null hypothesis? Is 0.09. It's greater than my acceptable level of error, my alpha error. Greater than 0.05, I failed to reject my null hypothesis. Let's go back and do it again. Descriptive statistics, compare means, single sample t-test. Let's compare it to a population with a mean of 7. Okay, well, this time I get a t-score that's quite a bit bigger, and my p-value, my probability of being wrong if I reject my null hypothesis, is less than 0.05. So now I reject my null hypothesis. Okay? Pretty easy when you use an SPSS. Just a matter of organizing the data correctly. Okay, so now let's see if we got any more twists and turns here. Okay, so now we have another situation. Okay, I'm going to open up another data file, which is paired samples. Okay, so now what is this? What is going on here? What's going on here is that we have 9 subjects. Remember when we looked at male and female? How many subjects did we have total in those 2 groups? We had 2 groups. How many subjects total, though, did we have? We had 18, right? We had 9 males and 9 females. So we had 18 subjects altogether. How many subjects do we have in this particular study? Well, let's think about what happened here. What they did was they gave a placebo to a subject for 2 weeks and then had him tell him whether or not there was whether how he was feeling or whether it reduced his pain. Then they gave him a drug for 2 weeks, the same person, and he reported whether or not he was feeling less pain. He reported, say, a pain scale or something like that, or they evaluated it some way. So each one of these lines represents the same person when they were on a placebo and when they were on a drug. So there's only 9 subjects here. This is a paired samples t-test. So now, in a lot of ways, this is better because when you have 2 independent samples, right, you could get more smokers in one group than in the other group. You could get more people that are overweight in one group than the other group. It's very hard to match the 2 groups for everything except the thing that you're interested in, right? You have a lot of things that could kind of like mess things up. In this case, we're comparing people to themselves. So now we can actually see for each individual whether that number went up or down for each individual, depending on whether he used a placebo or used a drug. The way they really would do this study is they would randomize it. So not everybody would get the placebo first and the drug second. So now really what we're looking at here is not really the value for the placebo or the value for the drug, the average for the placebo or the average for the drug. We're really looking for the differences. So what are the differences? It's equal to this minus this, placebo minus drug. Okay, so now I'm going to copy this down. Okay, there's all the differences, right? So now what we're really interested in, if there's no difference between the performance of the drug and the performance of the placebo, what would we expect the average difference to be? 0, right? We would expect the average difference to be 0 if the placebo and the drug work the same way, right? So let's find out what the average is. So the average is equal to 1.55. So so it looks actually like the I could have that minus that. So I could have changed it back and forth, but that's okay. So the deal here is now is that big enough number for me to say that the drug and the placebo are have a different result? Right? Is that a big? I can't tell if that's a big enough. I don't know how likely I would be to be wrong if I said, "Oh, that drug works now." I know that drug works now, right? So how am I going to analyze this? Well, I know that if there's no difference, then the average would be zero. I don't expect it to be zero because the chances of it being exactly zero are probably almost none, right? If we have enough subjects, right? So I just want to know if that's a big enough difference to be able to say that it's different from zero. So what would I use as my null hypothesis here? What do you guys think might be my null hypothesis here? How about starting with a null hypothesis that H null, that the difference is equal to zero. So what will my alternative hypothesis be? Difference is what? Is not equal to zero, right? Okay, so what I'm going to do now is I'm going to compare the average difference to a number. What number are we going to compare it to? Zero, right? What kind of test is this now? I went from 2 columns of numbers to 1 column. I'm doing a single sample t-test. A paired sample t-test is just a single sample t-test in disguise. Instead of comparing it to mean of another population, you're comparing the differences to zero. Okay, so let's give it a try. Okay, so I'm going to do it in SPSS. You could do it on here, or you could do it in SPSS. So I'm going to go to SPSS again. I'm going to say open data and paired sample t-test. Okay, so now here's placebo, here's drug, and I do need them in this. And see, this is subject 1, subject 2, subject 3. So this form, I do need them in as side-by-side columns. So I'm going to say analyze. It's still going to lock me out. Means. Yeah, I'll go back. Let me open the output window again. Analyze. Compare means. And paired sample t-test. Okay, now in this case, it's going to wait for me to put 2 variables in there, right? So notice there's 2 boxes here. I'm going to put the placebo in there, and then it's going to wait for another one because it can't do a paired sample t-test unless it has a second number. So I'm going to put that in there. Whoops, put that in there, and now I can say okay and go ahead with the analysis. Again, if my alpha error is 5%, I'm willing to accept 5% chance of being wrong. I'll leave 95 in there. If I want 1% chance of being wrong, I change that to 99. So I'm going to click OK. Let's see what we wind up getting. So here's our single sample t-test. Our mean is, the mean difference is 1.556, same as we got. Happens to be the standard deviation, the standard error. We could have calculated that in Excel, right, for the differences. That's the standard deviation of the differences, the mean of the differences, the standard error, which is just the standard deviation over the square root of 9 or 3, would give us that number. So now we would calculate our t-value. So our t-value is 1.75 with a significance of 0.12, a p-value of 0.12. Can I reject the null hypothesis? The p-value is 0.12. No, it's not less than 0.05. I fail to reject the null hypothesis. Right? Does that mean I accept the null hypothesis? No, I fail to reject it. Right? The whole point of this is to be able to say it's wrong. So now let me back this up a little bit. Degrees of freedom is 8, 9 minus 1, right? So this looks pretty much, look at this also. The 95% confidence interval for the difference of the means. In other words, we're 95% sure that the true mean of the differences of the entire population would have been between minus 0.5 and plus 3.6. What number is between those two? Zero. Zero is not outside of that confidence interval. That's another reason why I can't reject the null hypothesis. Okay, we can get away with this with a single sample test. Not really. We can't look at this idea of overlapping confidence intervals when we deal with independent samples, though. Like that gets a little messier. Yes.
So just relating this to something we were saying in the lecture at the end of class about p-values. So could you say that 0.122 does that mean there's a 12.2% chance of you getting
exactly right. There's a 12.2% chance of your getting this result, this big a difference, this result, this big a difference when the mean is not when the mean is equal to zero, right? When there is no difference between the placebo and the drug group, right? In other words, what you want is if you look at all the possible outcomes, you want to be in a situation where the difference between the two things you're comparing is the difference is large enough that you would get that big a difference less than 5% of the time if the null hypothesis were true, right? Because then you have a level of certainty that says that, well, within reason, I can say that they're different. Does that mean that if you find that your significance is 0.04 and you reject the null hypothesis, does that guarantee that the two populations have different means? No, it doesn't. You guys ever heard of the Worm Runner's Digest? There were a bunch of guys that were experimenting with RNA memory transfer in the 70s. And they were experimenting with planaria like little tiny worms, right? And these planaria would react to light. And they could actually train them to turn in one direction or another, in the direction of food, with stimulating them with light. And the planaria would learn to turn the right direction. So they would train planaria, then they put them in a blender and feed them to other planaria. And then they would test the other planaria to see if by eating the other planaria, whether or not they now could learn faster. And in their initial study, which they published somewhere, they proved, less than 5% chance that they were wrong, that the cannibal planaria learned faster than the naive planaria, right? Unfortunately, nobody could replicate that result. So these guys were determined to prove that this really works. They went on, and nobody would publish their work anymore after a while. So they started a magazine of their own called the Worm Runner's Digest. It was around for about 10 years. And they published their own work, and every offbeat, weird kind of analysis or study that no one else would publish, they published in that. And I don't, I've looked on the web, and I can find reference to it. I can't find any copies of it, though. So if any of you guys have any success with that, look up the Worm Runner's Digest and see if you can't find me a copy of it. So what does that go to prove? That goes to prove that, that when Canada does a study and finds out that rats get cancer from, a saccharin or whatever they were, and then 8 other people do studies and they can't replicate it, that sometimes that happens. 5% chance of being wrong means that 1 out of 20 studies that you do are wrong, right? So that's the world we live in, because if we wanted to be 100% certain, we would have to do studies that were so large, so massive, that we would just never get anything done, right? So that's why people do studies. Other people try to replicate them and then publish what they find as well. Okay, so there's one other thing I wanted to bring up, and then we'll call it a night, I guess. And that is, what about percentages, right? What about proportions? Okay, so there is a way to do that, and I just want to show you that in the file. We're not going to do it. We're going to actually do it a better way, kind of, when we go in the coming weeks. We're going to do, let's see, where is it? Where is that document? And let me find the window. There it is, right there.
Are we going to have to use Excel for tests and homework?
I think it's going to be whatever you want. I think that's basically. I might give you. For instance, I put up a homework already, but there's a homework number 5 already posted. It's due a week from now. It's a single sample t-test. I'm going to put up. I did a 2 sample t-test. But did I just put one that's 2 sample? I don't remember. I'll remember. I gave you the choice of doing it any way you wanted: Excel, SPSS, or R. I gave you the 3 data files for it. But I did give you a question where I posted a picture of an output from SPSS, and I asked you to interpret it. Okay, so on an exam, you can do it any way you want, but you still have to interpret the output one way or another. And you should be able to interpret the output for SPSS for all of us, just so at the end you can put on your resume, SPSS. right? Who knows? Maybe one day it'll get you a job or something like that. Okay, so what about proportions, right? What if we want to compare two proportions, right? The proportion of people that are voting Democratic versus the proportion of people who are voting Republican. Then there's a couple of other parties involved as well, right? So we have, what do we have? If we take a random sample of people and ask them which way are you voting, might have 43% Democrats, 42% Republicans, and so on and so forth. Well, how do we know whether that we really have a significant difference? Can we say that P for Democrats is equal to P for Republicans, or can we reject that idea and say that they're different? Well, one of the things it's going to depend on is how big the difference is in the two proportions. The other thing it's going to depend on is how variable the results are, the standard error, right? And if you look, we have a formula here. T is equal to the difference in the two proportions, P cap 1 and P cap 2 are the sample proportions, and then it's divided by this other number, this other formula, which basically represents what the standard error represented before. So you could calculate a t-score, right? So we're not going to do that here. When we move forward, we're going to organize this kind of data, like yes or no data, binomial data, into tables called crosstabs. Remember we did that with the diagnostic tests, right? We had 2 rows, 2 columns, right? So a proportion can be split up that way as well, right? So yes or no, you're a Democrat, in these 2 groups. So yes, 43 out of and 43 say yes, and 57 say no, and the other one is 43 say no, yes, and whatever, 57 say yes, and so on. So we can split it up into a 2-by-2 table, and then we do a different kind of test called chi-square. But we're going to deal with that later on. Really simple stuff. I mean, calculation-wise, it's really just basically pretty simple algebra when we actually do the calculation. But you can save yourself a lot of work and trouble when you're working with big data sets by learning how to use SPSS or R, and so on. Excel, basically, you're doing almost the same thing you're doing otherwise by hand. So it helps to a certain degree, but it really helps to use some of these higher level statistical programs. Okay, so I just want to make sure there's nobody online. You guys got any questions? So you have that stuff about the proportions here, but I wouldn't worry about that. I don't think it'll wind up on the exam. How are you guys doing online? Still awake? Okay, no questions. Okay, good. All right, good. I hope